Hello, I'm going to be explaining the two problems that I solved for the quiz, the pulley problems. Okay, so the first one asks, the figure shows a block of mass m resting on a 20-degree slope. The block has coefficients of friction U sub s 0.64 and U sub k 0.54 with the surface of the slope. It is connected using a very light string over an ideal pulley to a hanging block of mass 2 kilograms. The string above the slope pulls parallel to the surface. What is the minimum mass m so the system will remain at rest when it is released from rest? So the way that I solve this, we know that if it's at rest, we need to be looking for the mass of this object. So this is what it looks like without any of the annotations. So we know that the tension of the string goes up in this direction, and so does the acceleration, but the acceleration is not going to be very big considering that it's at rest. And then the tension of this block is holding up this block over here. It's tension 2. So the first thing I did was I understand that at rest, the weight of this second block is equal to the tension that it is being pulled up with. And at rest, that neither of them are moving, so the tension of at T2 will be equivalent to tension T1. So understanding that, we need to find ultimately this m, and we can do that by finding T1. So mg2 is easy to calculate. It's 2 times the gravity. So that'll be 19.62, and that is T2 and also equal to T1. So now that we have T1, we can plug it into the force equation. So the force of the first block is equal to the tension minus the friction. And it's equal to 0 because we know it's at rest. So the friction is equal to the tension. It's the same thing, but it would be in the negative direction, but it's the absolute value because it's force. So the friction is the coefficient of static energy times n, and we know that n is equal to mass times gravity. But in this case, we need to use the y component, which is mg cosine of theta, because of the way that the angle is here. It's not on the perfect x and y axis. It's slightly different because it's following this n. So we have to use the y component, which is mg cosine of theta. So friction is equal to the static coefficient times mg cosine of theta. So when we plug in all the numbers, we get 19.62 is equal to 0.64 times m, which is our unknown, times gravity times cosine of 20. And we get the mass is equal to 3.3 kilograms. And that's it. That's the answer for this problem. For our second problem, it's asking a system consisting of blocks, a light frictionless pulley, a frictionless incline, and a very light connecting wire is shown in the figure. The wires pull on the left-hand blocks parallel to the surface of the ramp. The 9-kilogram block accelerates downward when the system is gently released from rest. A, what is the magnitude of the acceleration of the 9-kilogram block? And B, what is the tension in the wire connecting the two blocks on the incline? Now, I will be honest in saying I don't think I did this question right. This is just how I did the question. So first we need to understand that the tension going up from this block is equivalent to M3G because it is their equivalent forces, but it is accelerating downward. So M3G will be slightly larger than T3. So some of the equivalents don't apply for this problem because it's not at rest. So T1 is T1 plus T2 is the total force of these two blocks over here, this system. And then I included the components of the weight. So to solve this, what I did was, I understand that there is no friction, So the force of the system of the first two blocks is equal to the tension of the first block plus the tension of the second block minus the friction. And we know that the friction is 0. So the tension of the first block is equal to the tension, sorry, so the force of the system is tension 1 plus tension 2. And that is equal to the acceleration of the total system. We know that the acceleration normally on a block that is on a ramp is mg sine of theta, because it would be the x component. However, because there's two objects, it would be mg1 sine of theta plus mg2 sine of theta to equal the total acceleration. So t1 plus t2 is equal to this exact thing. We just plug in the numbers. So the weight of block 1 is 6 times gravity times sine of 30 plus weight of block 2 sine of 30, which is equal to 49. So knowing the force of the system, we now know both of the tensions. So the force of the system on the right-hand side of this block is equal to the mass of the third block times gravity minus the tension of 3, because we know that the tension of 3 is smaller because the system is accelerating downward. So it's equal to also m3a, because it's accelerating downward, and that's the acceleration that we would be using on the y component. So 9 is the mass of that block, so we just plug in all the numbers. So 9 times 9.8 minus T3 is equal to 9 times acceleration, and then you simplify and you get A is equal to 4.35, and that's the acceleration downward. And then for part B, what I did was, in order to find the tension of the block, of the string that is holding up the block, I know that the force of just the first block would be equal to m1g sine of theta plus t1 minus friction. We know that friction is 0, so we can cross that out. And we know that the force is equal to mass times acceleration always. So we can make the equation equal to mass times acceleration of block 1 is equal to mass of block 1 times the gravity sine 30. This is all the x component of the weight, plus the tension that is holding up block 1. And once we plug in everything, we can solve for T1. I don't think I got this right. I don't think I got this question fully correct, but this is my process. I hope it's at least a little bit correct. Thank you.